We've talked about the idea of equilibrium in the vertical direction, like this example here, where a light bulb is hanging from a cord, and how, because it's not moving, we know that the forces in the y directions must all sum to zero. And we write that as sigma F is equal to zero. The force diagram shows us that the tension force up is equal and opposite to the weight force or gravitational force down. But what if we were to pull on the rope so that the rope or the cord itself was angled? Well, in that case, our force diagram would change slightly, and we would have that applied force to the left, and our tension force that's pulling upwards is now pulling up and to the right. It's pulling at an angle. Our downward tension force would still equal the weight of the light bulb, mg. And so in order to use the idea of equilibrium, we would now have to break that red arrow into components. By itself, it does not balance the applied force or the weight. It actually balances both. But to see that, we have to break that tension force into components. A force component that's to the right and a force component that is up. In the same way as the original situation, the up forces equal the down forces. But now it's just a component of tension that's pulling up, that's equaling the weight that's pulling down. And then we can also say sigma F in the x direction has to be zero as well. If our light bulb is not moving, if our knot or our connection point between everything is not moving, then the applied force pulling to the left has to be balanced by the other component of tension pulling to the right. Of course, to find those components, we would use some triangle trigonometry, but the key thing here is that the equilibrium idea holds true in all directions. Let's take a look at a couple examples to see how this looks when it's put into play. So the first thing I'm going to do is to create a force diagram from this picture. And you can draw right on the diagram, or you can sketch this off to the side. I'm gonna think about sketching it off to the side. This is going to be my key point. The dot that I've labeled here is where all the forces come together. There is weight pulling down. It's actually a tension force, but the tension would equal the amount of weight of the light bulb. So I'm going to think of it just as the weight of the light bulb pulling down. And then there is tension pulling at an angle up here. And then there also is an applied force of 50 newtons. That's perfectly horizontal. So what I'm going to do here is I'm going to look at both the x and the y direction and see if I can figure out any of these unknowns. Let's start with the tension force. I'm going to redraw this in red since it's red in the original diagram. There's an angle that's given to me. It's this angle up here, and I'd like that to be inside of a triangle. This red arrow is at a diagonal. It's going to be the hypotenuse of a right triangle. And I could either draw my right triangle down here, or I could draw it up here. I really kind of have a choice. I'm going to choose to draw it at the top because that's the angle that I know. So I'm going to go ahead and put in some components. So my tension force pulls up and to the right, and so my components are also up and to the right, and then my angle that I know is right here. Okay, so there's my right triangle that I can work with. And the key thing here is that there are a number of forces that I can see in my picture. The up forces have to equal the down forces, and the left forces have to equal the right forces. So this should equal this component, and the weight here should equal the other component. So I'll start with the left equals right. Right, so the sum of the forces in the x direction have to all balance. So that means that the F sub p to the left has to equal this, which I'll call T sub x, to the right. So T sub x must also be 50 newtons. That's the thinking that's involved here. All right, well now I have enough parts of this triangle to actually solve it. I have the hypotenuse, I have the side that's adjacent to my angle. All right, so I've got hypotenuse, I've got adjacent, that is the ka of SOHCAHTOA. And so we'll say that the cosine of 36 degrees has to equal the adjacent 50 over the tension force. And then I like to use an algebra trick to solve for that tension force. Since it's in the denominator, I'm going to switch along the diagonal, and I can say that tension would equal 50 divided by the cosine of 36. I should be getting a number that's bigger than 50. That's always a good hint. And this comes out to be 61.8. That is a tension force that I'm finding, so it would be labeled in newtons. And then the other part of the problem was to determine the mass of the light fixture. So let's switch gears here. Let me switch to blue so we can find it. So this is now what I'm going to try to find. I'll first find the weight force, and then I'll go ahead and use that to determine a mass. And to do that, I could choose to do a different trig function, okay? It's this other side that I'm trying to find. Or we could do the Pythagorean theorem, because now that we have found tension, we know the hypotenuse. So let's go ahead and use a Pythagorean theorem. We'll call this f sub y. Okay, that's the thing we're trying to find. So 50 squared plus f sub y squared should equal 61.8 squared. And I'd work my way through the Pythagorean theorem here by squaring the 61.8 and then subtracting whatever 50 squared is, and then square rooting my answer. And after I do that, we end up with f sub y equal to 36.3. And again, that is a force, so that would be in newtons. I'm not quite done though, because I was trying to find the mass, but since this is f sub y pulling up, and up has to equal down during equilibrium, this is also the gravitational force that's pulling down on that light bulb. And so if I want to find the mass, I would just take that force and divide by g. We'll assume we're on Earth. And so our answer would come out to be 3.63. And now that I found mass, this would be in kilograms. In other situations, both of the ropes or sections of rope that are supporting the hanging mass are at an angle. So rather than having one horizontal and one diagonal, they are both diagonal. And we'll focus on situations right now where everything is symmetrical. The main idea is to take a situation like this, and again to draw a free body diagram. So we have the weight force pulling down, which I don't know. We're trying to find the mass. So after we figure out the downward force, we'll divide by 10 to find mass. And then we also have two tension forces pulling to the sides, but not exactly the sides. They are pulling somewhat up and somewhat left and right. And so what we want to do is we want to break these diagonal forces into components. I do always suggest that you go out and then up when building these triangles. And so really what we want to do is we want to figure out this force right here, which is going to be the same as this one since it's a symmetrical situation. And when I add those together, or double one of them, that's going to tell me this downward force, and I'll be able to find the mass. So we just need an angle. Since this is 28 on the original problem, if I take 180 minus 128 and divide that by 2, it'll tell me what the angle is on both sides, again, because it's a symmetrical system, and this comes out to be 26. Now, it would actually be true that the f of x forces on both sides would also equal each other. Although that's true, though, that's not necessary in this problem. So we'll just focus on the fact that the forces in the y direction must balance out to 0. So we have 2 upward forces, f sub y, minus the downward force of weight equaling 0, or the 2 ups have to equal the down. The force F of y can be found directly, though. That's going to be the tension force of 280 times the sine of 26. And so that will equal our mass times 10. And when we go through and solve this all the way through, we'll get that our mass is 24.5. It's not the only way to solve this question, but it's a nice clean solution that uses, again, the fact that the sum of the forces is 0.